Good morning, students. So in previous class we have discussed about capacitor, capacitance and its unit and dimensions. Okay. So in this lecture we discuss about an important thing, that is dielectrics. Okay. So everyone already used the dielectric concept in electric field and electric force. Okay, and we define a dielectric constant K that equals to force in air divided by force in a medium. Okay, or simply we can say in terms of electric field, that is electric field in air divided by electric field in medium. Okay, that is the term that we use, the dielectric constant. And also we find if we place a dielectric in between the two charges, then electric field continuously decreases. Okay, so in this lecture we discuss more about the dielectrics. Okay, so what do we mean by dielectrics? What do we mean by dielectrics? Okay, so generally when we consider a dielectric, first things that comes to mind, it is a non-conducting material, or simply we can say it is a insulator type material. Okay, so a dielectric mainly that is a non-conducting material in which equal and opposite induced charges produced in the opposite phase when we apply an electric field. So that's why we can say a dielectric is the non-conducting material in which equal and opposite charges, equal and opposite induced charges produced in the opposite phase due to application of electric field, due to application of electric field. Okay, so we mark this point more vividly. Okay, due to application of electric field is called dielectrics. से पॉइंट को हम एनालिसिस करबा बोलसे जनरली हम कहूचे जो नॉन कंडक्टिंग मटेरियल टा हम यूचे दैट नॉन कंडक्टिंग मटेरियल इज नोन एज dielectrics. Okay, so if we observe a dielectric, we find when we place in between the electric field, there will be production of equal and opposite charges in the opposite phase of the material. Okay, so material रे दीटा opposite phase रे equal और opposite रे charge arise होबो जेतेबेला हम इलेक्ट्रिक फील्ड को अप्लाई करबा. ओके, जदि हम इलेक्ट्रिक फील्ड रे ताको न रखिबा, जदि गोटे डाइलेक्ट्रिक को हम इलेक्ट्रिक फील्ड रे न रखिबा ताहले तार बिहेवियर केमति हम पाइबा. जदि हम गोटे डाइलेक्ट्रिक इन द एब्सेंस ऑफ इलेक्ट्रिक फील्ड ऑब्जर्व करबा, सपोज दिस वन इज अ डाइलेक्ट्रिक मटेरियल. ओके, सो इनसाइड द डाइलेक्ट्रिक मटेरियल देयर इज द presence of electric dipoles. Okay, but the electric dipoles are randomly oriented. Okay, so if you draw the electric dipoles like, suppose these are my electric dipoles that are present in between the dielectric in the absence of electric field. Okay, so electric dipole means we can say here there is a presence of equal and opposite charges, so plus minus, so like this they are randomly oriented inside the dielectric. Okay, so this one is a dielectric in the absence of electric field. Dielectric in the absence of electric field. In the absence of electric field means we can say here electric field is zero. External electric field is zero. Okay, E 0 I mention here external electric field. So external electric field is 0, and if you observe, as the dipoles are randomly oriented, that's why the net electric dipole moment becomes 0. All the dipoles are randomly oriented, and if we make these dipoles to a common point, then we find as they are arbitrary direction, as they represent like arbitrary direction starting from a common point, so that's why we can say net dipole moment becomes 0. Okay, so here we can write, in the absence of electric field, the net dipole moment becomes 0. Okay, so electric field is 0, and the electric field vector taken scalar form, so net dipole moment becomes 0 for a dielectric in the absence of electric field. But what we say, when you place in the electric field, there is a production of equal and opposite charges in the opposite pairs. Okay, suppose I place the dielectric material in between the plates of two electric fields. So this one is plus, okay, and this one is minus, and the medium between them is now air. Okay, so that's why electric field is, suppose, E naught. Electric field is E naught. Okay, and that is directed from plus to minus. Okay, so if we place that dielectric material in between this electric field, observe here, if I place the dielectric material in between the electric field, what happens? There is the formation of electric polarization. There is formation of electric polarization. Okay, so that's why I can hear that is dielectric and electric polarization. Electric polarization. Okay, so there is continuous formation of electric polarization. Electric polarization means that is the arrangement of these electric dipoles in the electric field. Okay, so that's why we can mark here the electric dipoles arranged like this. Suppose these are the dipoles, okay, and as this side is positive, so it takes all the negative charges of the dielectric, okay, and this becomes positive. Okay, as this one is positive, so this becomes negative and this becomes positive. So these are the dipoles. This one is positive means this one is negative and this one is positive. So if you observe at one face, okay, look at the position. Look at the position. There is a continuous arrangement of negative charge in the one face, and there is continuous arrangement of positive charge in opposite face, and magnitude of negative charge is equal to magnitude of the positive charge. So we can say there is a induction of charge. There is a induction of charge on the opposite face of the dielectric when we place in between the electric field. Okay, in between the electric field, and that concept is known as dielectric. So dielectric are the non-conducting materials in which the equal and opposite charges are produced in the opposite face of the material because of application of electric field. Understand? Now come to the part of electric polarization. Okay, so electric polarization means, we say, electric polarization, that is the arrangement of electric dipoles in a uniform electric field. Okay, so if we place electric polarization, so electric polarization means the process of induction of equal and opposite charges on the two opposite face of the dielectric due to the application of electric field. Okay, so polarization of a dielectric is the process of inducing equal and opposite charges in the opposite face of the dielectric, opposite faces of the dielectric on the application of electric field. Understand? Okay, this process is called electric polarization. So we can take the concept of the figure that we have taken in the dielectric. ओके देख ये आम कौन कौचे ना डाइलेक्ट्रिक जो आम एब्सेंस ऑफ इलेक्ट्रिक फील्ड बा विदाउट इलेक्ट्रिक फील्ड ऑब्जर्व करूचे से केस रे मोर कौन आसुची ऑल द डाइपोल्स रैंडमली ओरिएंटेड एंड एज ऑल द डाइपोल्स रैंडमली ओरिएंटेड इनसाइड द डाइलेक्ट्रिक सो नेट डाइपोल मोमेंट इज जीरो. Net dipole moment is zero. But if we place dielectric in the presence of electric field, this is figure is the dielectric in the presence of electric field. Okay, as we apply the electric field, what happens, there is a continuous arrangement of electric dipoles and the positive side, the positive plate of the applied electric field pulls all the negative charges of the dielectric towards itself, whereas the negative side will pulls all the positive charges of the dielectric. Okay, so that's why there is the electric polarization, and if because of the electric polarization all the dipoles arrange in a continuous manner, arranged in a regular order. As the dipoles are arranged in a regular order, that's why we say the net dipole moment cannot be zero. Net dipole moment cannot be zero. Okay, so as net dipole moment cannot be zero inside the dielectric, means we can say there must be a induction of electric field. Okay, so that's why you can say one phase becomes the negative charge density. So right here sigma p. What is the sigma p? Sigma p means it is the polarized surface charge density or polarized charge density. Okay, polarized charge density of the dielectric, and this side there is a production of plus sigma p. Okay, plus sigma p, and here there is a p means that is the polarized. Okay, polarized surface charge density, and here this is also polarized surface charge density. Okay, so as both the plates makes the arrangement of the charges, that's why there is a formation of electric field. There is a formation of electric field, and that electric field we mark as polarized electric field. Okay, that electric field we term as polarized electric field. Okay, so the polarized electric field, that is we mark here EP, that is polarized electric field. Okay, and when we measure the net electric field here, okay, the net electric field if we measure, that is called reduced electric field inside the dielectric. The net electric field in the side of dielectric is known as reduced electric field inside the dielectric. Okay, the net electric field inside of the dielectric is known as reduced electric field is known as reduced electric field. Okay, and that is taken as E. That is taken as E. So look at here. This one is the external applied electric field E, and this one is the induced electric field or polarized electric field. And if we mark, if you observe, the induced electric field and the applied electric field are opposite to each other, and as the field are opposite to each other, so reduced electric field, the reduced electric field E becomes E naught minus EP, E equal to E naught minus EP. This will give the expression for reduced electric field inside the dielectric. Okay, so reduced electric field inside the dielectric material. Understand? If I take sigma is the surface charge density, if sigma is the surface charge density of the applied electric field and sigma p is the induced surface charge density of the dielectric, so as sigma p is the induced electric field for the dielectric, that's why we can say already we have obtained in between the plates of the electric field, the resultant electric field that equal to E equal to sigma by epsilon 0, net electric field in between the two plates that is E naught equal to sigma by epsilon naught. And if I find sigma p is the polarized surface density, then EP equals to sigma p by epsilon naught, sigma p by epsilon naught. So that's why we can write here the net or the reduced electric field E equals to sigma by epsilon naught minus sigma p by epsilon naught. So that equals to E equal to sigma minus sigma p divided by epsilon naught. Okay, so this will give an expression of electric field in terms of surface charge density and induced surface charge density. Okay. So in the next class we will discuss about the susceptibility, polarization vector and their relation. Okay. So this is all about today. Thank you.